Yes, I'd like to introduce Wilmer Leal, who's going to talk about temporal time-varying data. And I think this is a great paper with all these great thoughts.
Okay, thank you, James, for the introduction. Hi, everyone. I want to tell you today about some of the ideas that we have about how to start building a unified theory of temporal data. And this is joint work with Benjamin Merlin Bumpus, James Fairbanks, who is here, Martti, Karvonen, who is also here, and Frédéric Simard. So all this started because we were taking a look at this emerging field of temporal networks, and then we thought that they have great ideas there, very cool problems, and then we were wondering if we could write a theory, a categorical theory about these temporal networks, and also along the way solve some of the issues that we think, or some of the issues that we believe that this field has. And then we put together this list of desiderata that we believe that any mature theory of temporal data should satisfy. And the first one is that by taking a look at the literature in temporal networks, they are based on objects. There is a more or less a good definition of what a temporal network is, but there is no good definition of what a morphism is. And this is important to us because in our opinion, any mature theory of temporal data should be invariant under isomorphism, for instance. And then we are going to address this. There are some spoilers in this list. The second thing is that, yeah, there are some people that are working on temporal networks that is just studying how networks change over time, but there are also people that are working on studying how topological spaces and other mathematical structures change over time. And we were wondering if we can be inspired by network theory, by temporal network theory, to build a unified theory that can be applied to more or less any mathematical structure. Also, another thing that we observe is that there are like these two perspectives all the time. One of them is that they want to calculate accumulated patterns, but also they want to compute patterns that persist over time. And then they change representation all the time. And we were wondering if we can formalize these two perspectives and then find a connection between them. And we did, and this is also a spoiler that I bring. There is an adjunction between them. This is a fantastic spoiler then. Hope that you guys pay a lot of attention to this. And then there is this other problem that we have lots of static ideas like or properties like being a path. And then the question is how can you lift this static property to the temporal counterpart? Because in the literature there are many versions and they are more or less disconnected from one another. So we want to accomplish also this as a systematic way of temporalizing properties. And finally, we were also wondering how we can formally study connections between temporal data and dynamical systems. Okay, so but what do I mean by temporal networks or temporal data? These are some examples that we are taking from this huge and growing number of data sets that are generated by an underlying dynamics. And these examples are taken from network theory or from temporal network theory. There are human and animal proximity networks, human communication networks, collaboration networks, economic networks, biological, chemical networks, epidemiological networks, and so on. So we might be tempted to believe that then a temporal network is just a sequence or a mere sequence of snapshots, each of them associated to, like this is just the relations, if that is what you are looking at, the relations of that are present in time 1, the relations that are present in time 2, and the relations that are present in time 3. But we claim that this is not enough. We also need information about that is relating what happens in time 1, from passing from time 1 to time 2. Otherwise, it can be very difficult. It can actually be very frustrating, right? If we don't have that information over this. So in this case, I don't know. I have tried. I wasn't able to actually draw the cat. We need the information. We need more than the snapshots. We need a narrative that is telling us what is going on from the first snapshot to the second one. And then we claim that we can encode all this information, this narrative, if we use not only the snapshots, which are here. In this case, the data structure is just sets, the set of companies, let's say, that we observe in time 1, the ones that we observe in time 2, and the ones that we observe in time 3. And these are just morphisms in the category of sets. These are also sets. And then we are going to use these spans, that is those sets and those functions to create a narrative. For instance, if you see here, A1 and companies A1 and A2, they disappear in the second snapshot. And the company B1 also disappears in the second snapshot. And then there are 2 that appear, A and B2. But then we can codify, for instance, this mechanism or this phenomena. And is that if this is the canonical inclusion, and this over here is mapping A1 and A2 to A, then we can see that, or we can encode the narrative that the company A1 and A2, they merge to form a company A. While on the other hand, using the same functions, we know that actually B1 actually disappeared and company B2 actually appeared, and so on. So what we are creating here is a narrative, and this is capturing much more information that we need, that we want from the underlying dynamics. So of course, this is not limited to the category of sets. We can do this also with other aspects of the data, perhaps aspects that are relational in nature, or we can actually use the physical positions and play around with metric spaces and so on, and then use all these to speculate about what happened with these companies over time, which is what people do in data analysis anyway. Okay, so yeah, that's very cool. Now we have part of the data structure that we want, but we are also interested in computing long-term relationships. That is, in our example, which companies actually persisted over the course of the 3 years or longer intervals of time. And this is the data structure that we had before. And for us here, we know that in order to do that, that reduces or translates just to compute the pullback of this diagram over here. And then we have computed not only the data, but also the relations that persisted over time. Okay, cool. So this looks more like the data structure that we are looking for to compute persisting patterns. But we also, and in all these theories of temporal data, they're also obviously interested in computing data that is accumulated, data and relations that are accumulated over time. So we are very quickly going to change the representation that we had, and we are not longer using the spans to relate to snapshots, but we are going to use these spans to encode that narrative. And now we can compute the patterns, that is the data, and also relationship that accumulated over time by just computing the push out of this diagram. That will tell us what are the companies and the relations that were accumulated over the span of these 3 years. Okay, cool. So we have a data structure that sounds reasonable, and now we have to write it down in categorical terms. And it looks like what we have is a functor that is defined on certain category of time that seems to look like this. There are some close intervals of time. There is a functor that is associating the snapshots to each of these points, and also to this second row. This is just data, and then from then onwards, it's just computing stuff. It's a data structure that allows us to compute, in this case, persistent patterns. How do we formalize this? Then for that, we are gonna borrow some ideas from Schultz, Spivak, and Vasilakopoulos on interval categories. So the category of intervals just has closed intervals as objects and some morphisms, orientation preserving isometries. And these intervals are of non-negative real numbers. And we can also get a discrete interval category if we just restrict to the natural numbers. And moreover, we can turn these categories into sites by using the Johnson coverage, which is just telling us what are the covers or what are the partitions in this case that are admissible for the objects of our time category. And in this case, it's just a point P, or a cover is just a couple of intervals or a partition of this interval into 2 of them for every P that is between A and B. That is all. but as you said, as you saw in the in one of my slides, our time category is much simpler than this. So we are going to use this simpler definition that says that we are going to have a full subcategory, which is specifically a joint similarities of the subobject poset of the real number. So this is just closed intervals as objects and inclusion maps as morphisms. That is our category. And we can have it in both versions for the real numbers or for the natural numbers as well. And this lemma is just telling us that we can turn also this category into a site by defining the Johnson coverage. Okay, cool. So we already have this category over here, and now we are ready to define our data structure, in this case, for the persistent case, for the data structure that is computing patterns that persist over time. So remember that here we need to take pullbacks. Then our definition goes like this. We have a category of time, which could be the reals or the natural numbers, or the category of intervals of reals or natural numbers. And we have this category D, which has pullbacks. And then a D value chief on T is just a pre-chief, which has the extra condition that for any closed interval of time and any cover of this interval, we are going to define the data that is associated to AB as this pullback. And that's it. Okay, dually, we can do the same for the other data structure, for the other flavor, or for the other perspective, for the cumulative perspective, as follows. Here, remember that we have to take push outs. Then we start again with our time category, and then we take a category that has push outs, and we say that the D value cochief on T is just a cooperative, is just a functor from the time category to D that satisfies the extra condition, again, that given any interval and any cover of this interval, the data that is associated to this interval is just going to be computed via this push out. Okay, so those are our propositions that you can take as the definitions for our data structures. And now we are going to take, for instance, all these are the chiefs that, remember that they are used for computing persistent patterns, and these are the cochiefs that are used to compute accumulated patterns. Then we are going to take all of these, all the chiefs, and we are going to form a category with this, which we are going to denote as the persistent B narratives. And this is our notation, and we are going to also take these cochiefs over here, and we are going to form a category that we are going to call the cumulative D narratives. And that's it. Okay, so now we have these two categories. Again, one representing, one for narratives where it makes sense to ask about persistent patterns, and one where it makes sense to ask about cumulative patterns. And now the question is how they are related formally. And then we prove this theorem that says that if we have a category D that has both limits and colimits, then there is a functor that a functor P that given a narrative, a cumulative narrative in D, give us or better said, the passing from cumulative to persistent is functorial, and passing from persistent to cumulative is also functorial, and moreover there is this adjunction. Okay, and just to give you an idea of how this works, I'm going to tell you how these functors P and K work on objects. So we take a cumulative D narrative over here, which is just a which is just this cochief over here, f hat, and we have to define a chief, like an object that lives over here. And this chief is going to be defined on objects as follows. So we take an interval of time, a closed interval of time A, and all this complicated notation from here to here just says that in that particular closed interval defines as sub-semi-lattice in the category of time. Just consider all the sub-intervals and all the inclusion maps. So you have that semi-lattice. And now you use f hat to assign the data. And then you get a diagram that is in D. But D has limits. So you just compute the limit of this. Okay? So this is giving you this is giving you just somehow some, if this f hat is a cochief, then it's a data structure that is computing accumulated stuff, and then you are taking a limit, you are going through the things that persisted on this diagram in D. Okay. Dually, K is defined as follows. So again, we take a chief like this, F, and then we have to define a co-chief over here, and it's just gonna be given like this again. So you take an interval of time. Again, this defines sub-semilatives, which is just the subintervals of A, B, and the inclusion maps. You assign the data with F. This gives you a diagram in D, and then you compute the colimit of this diagram. That's how it works on objects. We can discuss later if you want how this works on morphisms. But it's very easy because all the objects there are going to be limits and colimits, and there will be unique maps all the time. Okay, so now is it possible to write these the things that you have in temporal network, in the theory of temporal network, written in terms of graph theory, in terms of this language? And the answer is yes. This is one of the definitions that is very popular, which is, it just says that a temporal network, given a set of that is representing time, that could be the natural numbers or reals, and then a temporal network is this tuple that is a graph and 4 functions. These functions are just going to tell you if a given edge is present or not at a given time. This is telling you if a vertex is present at a given time or not, and these over here are latencies that are telling you what is the time that takes to traverse an edge or to traverse a vertex. It can change over time. So you take an edge and a time, and then you are going to assign this latency. Okay, so this definition is okay and it's very popular, but it has some issues. For instance, you can have an edge and a time where the vertex is actually not present and stuff like that. So can we write this in terms of in our language? And the answer is yes. For that, just consider the monoid of natural numbers, viewed as a graph with a single vertex, but we are going to write it as a functor on the schema of graphs, just the 2 objects and the 2 maps, source and target maps. And then we are going to take this category, which is the category of all directed graphs, and we are going to compute the slice category over this functor over here. And that give us a category that has pairs of objects. One graph, the directed graph that we started with, and now a graph homomorphism that is assigning a natural number label to each edge. So what we did here was just to build directed graphs that have latencies on the edges. And now, if we take narratives that are valued in this category, and this category has limits. Actually, this over here is a topos, and then we take a slice over this object. This is also a topos, and therefore this is a topos, and therefore we have limits and colimits. We can do it. These narratives can be interpreted as time-varying graphs whose edges come equipped with latencies. Okay, so we can do that. And you can use the same strategy as a recipe for doing the same for other kinds of temporal objects like temporal graphs, networks, reflexive graphs, symmetric and reflexive graphs, Petri nets, and so on. Okay, so this was very powerful. Then let me tell you 2 more ideas very quickly. Now, another question is how to change, like perhaps you are doing data analysis on using graphs or topological spaces to represent your data, but now you are asking a question that in such a way that you have to go to another category, like, I don't know, like groups or something like that. Then you need a way to change this base category. And then it goes like this. If you have C and D, there are categories with limits, for instance, and you have, and this is the anytime category. And if you have a functor that goes from C to D that is continuous, that is going to send these limits into limits, then the post-composition with K determines a functor. That in this case, for instance, if we apply that to the persistent case, we can lift this functor to the temporal case that goes from the persistent narratives in C to the persistent narratives in D. But dually, you can do the same if this functor is, for instance, co-continuous, then you can go from the cumulative narratives in C to the cumulative narratives in D. Okay, great. This is a simple idea, but let's use it. So another simple idea is that any class P of objects in C can be identified with a subcategory that looks like this, where this functor is just picking the objects of C that have the property P. And then if this functor again is co-continuous, we can use the proposition that I just showed you and lift this property to the temporal counterpart and somehow define a full, define a subcategory or a subclass of these narratives that have the property P. For example, if we take this functor over here to be this functor that is just choosing paths from graphs, then we can lift this functor to this functor that is a static property, the property of being a path, to something temporal, which is the cumulative narratives that are paths. Okay, so we can do that. It's a very simple idea, and let me finish with this. I'm going to use that idea, that simple idea of defining, like that simple but also very powerful idea, because that was a systematic way of lifting static properties to temporal properties. And now let me use that in conjunction with the adjunction that we proved to do something very nice. We are going to prove that the cumulative temporal tree problem is equivalent to the persistent temporal path problem. And then we can discuss why this is so interesting. But then consider this adjunction over here. And then let's now use the change of base proposition that I showed and apply that to this full subcategory, which is just choosing trees from graphs. All this is happening, all these the arrows in this slide are monos. I'm not gonna be saying mono all the time. And then this gives you the following. Here we have just this functor, it's just this functor over here lifted to the cumulative from the static to the temporal to these cumulative narratives. And then this functor over here is just K. It is just one of the functors from the adjunction. And this is the other functor that I showed in one of the examples, which is just choosing the temporal persistent paths from the persistent graphs, from the persistent narrative of graphs. And notice that this is forming a diagram in CAT. This arrow over here and this arrow over here. You have the diagram in CAT, and then if you compute the pullback of this diagram in CAT, what you get is a category which objects are pairs, and one of them is a cumulative tree, the other one is a persistent path, but in such a way that when you go down and you think of them as cumulative graph narratives, they coincide, and they actually coincide. They are the same narrative. So this is very cool. This equivalence, because on the one hand, trees are objects that are much more complex than paths. On the other, and you are accumulating them. So the memory that you are using to store them is growing and growing and growing, while this problem over here is much simpler. They are just paths, and you are taking sort of intersections and so on. So the memory to solve this problem is increasing. So this is very cool stuff. And then that's it. This is what we have accomplished. We have now these categories of temporal data. So we have not only temporal networks, but temporal, whatever is your mathematical structure that has limits and co-limits. We have objects and morphisms. This is object agnostic, so you can copy this theory and use it to other categories that you like. We have the cumulative and the persistent perspectives. They are related formally via this adjunction. We have a systematic way of lifting static properties to the temporal counterparts, and now also we gave a very small step forwards in connecting temporal data theory with dynamical systems. Now that this theory is written in the language of chips.
Thanks, Wilmer. Happy to take questions.
Yeah, I wanted to have a more abstract definition of the type categories. You said it's like a subcategory of real intervals. The more abstract way of defining.
yeah, for the purposes of data analysis, we believe that this is enough, right? Even probably just natural numbers is enough. Just thinking in an implementation in code, but I don't know. Like obviously, the next more general definition would be something like this. But I guess that the answer is it depends on what is the purpose that you have in mind, and that way we chose a path to generalize it. But
time is aligned with something like a versioning system.
yeah, like we spent a lot of time thinking about this, like how to define a time for us, if it was a line, if it was just a poset, or even if it was just a pre-order and it was cyclic. And it turns out that there are philosophical discussions about time being cyclic and so on. So yeah, you can find a model and then start working. But for the purpose of data, I think that this is like the sweet spot.
I wonder about kind of temporal logic as such, right? You know, we would like to kind of connect this scaffolds of intervals with what happens with traditional or even better constructed temporal logic. Someone had kind of think about it.
No, that's a lovely idea, and I haven't thought about this, but now that you are here, we can probably discuss it. I will be very happy to discuss with you this. Yeah. Okay. Thanks for the question.
I have a follow-up to that. The adjunction. Can you say something about how that adjunction relates to like logical quantifiers?
To logical quantifiers, yeah, I think that like in my mind when we were working on this, somehow we were on the cumulative side. We are taking sort of unions, an equivalence relation, or something like that, and on the persistent side, we are taking intersection, which is just like on one hand there is the for all, which is for the persistent case, and on the other one there is there exists this pattern at this time of time, and so on. So that's how it works in my mind. But obviously, like it has to be more precise. But yeah, that's the intuition.
Yeah, so when you if you have any condition on your time varying data, not
Sorry?
Do you have any condition on your time varying data that determines how much it won't be a sheet for this. Essentially rely on using the coverage, one that allows you to
That's an interesting question. Okay, I think that I will have to think. I understand the problem, and you're right. But I guess that I will have to think more about the modification that you'd have to do to include such a phenomena. Yeah. But thank you for pointing that out. Yeah.
Is like a sheet on the residual category value is that the same as a pointer from the real poset or the non-measured real poset into span?
Yeah. Okay. So that's we were having this discussion before coming here because you know Ben and one of the authors and how he feels about strongly about cheats. Yeah, and
this is part of why I asked.
Yeah. Okay. Yeah. He said that there was going to be this discussion over here. So I don't know if you are going to accept this answer, but it's spans and cost spans probably perhaps, but also with this extra condition of this gluing condition, and this has a name, right? Like these are chips and co-chips. So I guess that you can choose You can say that they are spans and co-spans with this growing condition, or that they are chips. I am not going to take a side. I'm okay with both.
I think that this is related to David's question too, that the category you're tapping into is combinatorial, then like you can't have this smoothness. Because like if you're doing graphs, like you either get an edge or you delete an edge. There's no smoothness in graph. And so I think these are all related. The kind of spans are enough if either time is discrete or space is discrete, and I think these are all.
I guess going into the Larry, we would have thing based on this thing. Answer to David's question, we use a coverage where you kind of with process intervals and increase, and I think that and then for LRI, different coverage. And the bigger coverage doesn't include both the little patches. But you can, that's just a right, that's a modality. I think this actually the span someone said is a street ownership coverage. Pseudo yeah, cool.
I think that's our time. So happy lunch, everybody.